Okay. All right. You got a copy of your first test, and if you have any questions about it, please bring those forward. Now, legitimate questions are what you mean by this, or less than legitimate questions are how do you do this problem? No, I won't answer that one. That's what the test is all about. But those questions are very similar to the ones I have in the homework exercises. So I'll work any homework exercise, find it, and as long as it's not so close to being the same problem, but we'll find one that's a little different. And if you do find one that's too close, so you can use that as a guide. So sheet for having it in a week, you can have all the time you need, but I just don't want you still holding that one out when I get ready to give you this one. Now this is a long chapter. This chapter is first order differential equation. Now if you remember, we classify differential equations several ways. What are some of those ways? Okay, you can have linear or nonlinear. Okay, we're going to talk about mostly linear in this chapter, but not all. I mean, that's just a little piece of this. Any others? Classifications? Say again? I can't hear. Ordinary or partial, yes. We're dealing only with ordinary, okay? What's another classification? Look at the second. Order, exactly. And in this chapter, we're dealing with first order differential equations. What do we mean by that? Okay, the maximum derivative you're going to have is first derivative. Okay? Now, there's 6 sections here. The first one is one of these touchy-feely ones that we're not going to really do much, but hopefully it'll give you an idea of what's going on. Then we'll look at several types. First, separable. Second, linear. Then exact. And then solutions by substitutions, okay? And then we'll look at a little bit of numerical methods. Not a lot, but a little bit. That, remember, is one of the things in the course description. I doubt if we're going to get the chapter on that, but we'll at least hit it here. Okay, so let's look first at 2.1, solution curves without a solution, okay? Now, you'll find, and this don't mean for it to be sounding sort of discouraging, but it's reality, okay? In real life, you will run into differential equations, and usually they're in pretty complicated situations, and most of the time, not solvable, okay? You can't really get a solution. Now, we're going to give you as many keys and clues and helps to do what you can with what you got, but in reality, in the real world, most of them probably are going to be close to non-solvable. But does that mean you can't learn something from them? Well, a first-order differential equation can look like this. It won't always. dy dx is equal to some function of both x and y. Okay? Now, remember, even though you have two variables here, one is dependent and one is independent. If you had two independent variables, then you're talking about partial differential equations. We're not going there. We're doing the ordinary. So even though it's a function of both x and y, remember x is the independent variable, y is dependent. Okay? But that's one way a differential equation can look. Okay? Remind me, what is, and by the way, that function can be one hairy-looking mess that maybe you can't even know how you took a derivative and got that mess, okay? But guess what? You can still do something with it. What does dy dx stand for? The derivative. And what does the derivative tell you? Of any old function out there. Of what? okay, in a sense, the slope of the tangent line to that function at any point, right? Well, guess what? This is some function, some combination of addition, subtraction, multiplication, division, powers, roots, transcendental functions, some sort of things, but they're all functions, things that you can do things with. And you can pick any old x and any old y. That's a point on the graph, right? X, Y, right there, there it is. Or over here, or wherever it happens to be. That thing. And then you can plug that value, -3/17, whatever point you choose, into that function and evaluate it, right? Functions are evaluable, right? Not invaluable, evaluable, okay? You can evaluate it. Well, then what do you got? A number. You plug in numbers, do the function, you get a number. What does that number represent? The slope of the tangent line at that point. Okay, that could be a +1, a -2/3, you know, whatever, but you have, at that point, you know the slope of that tangent line. So that does give you information. You may not be able to solve it, but you have the slope of the tangent line there. That's what we're going to be doing here, and we call those direction fields. Okay? Let's see. You do or don't have a book? You do. Okay. All right. Just making sure. Okay. 2.1.1 is talking about these direction fields, and they say some fundamental questions. A derivative dy dx of a differential function y is equal to y of x gives the slopes of the tangent line at the points on the graph. That's what we just were talking about. Okay? So you can think of those as slope functions, if nothing else. Sometimes those, especially if this was a t in the bottom, that's your independent variable, then that could be a rate. Okay? This is velocity at that point, acceleration at that point, rate at which you're using gasoline or your energy or whatever. It could be a rate. Okay? So, you don't know the curve, but you do know the slope of the curve. And you do know the slope of the curve follows that curve pretty well. I mean, let's go to this line, okay? Let's say there's our point here, and we get a slope. That means the curve could be doing this, it could be doing that, but you know, whatever it's doing, it's pretty close to that at that point, okay? So we don't know what curve it is, but we do know generally close to what it's doing at that point. If that slope was here or here or here, you know the curve has to be matching that. Okay. So that's what the slope says. The direction field, if you do a whole bunch of these, then you get an idea of what the trends are. Okay? Now remember from the last section, okay? The last chapter. A lot of these differential equations, when you can deal with them, you get a family of solutions. Anytime you have those constants in there, different constants will give you different curves. Remember, that was from last time. So you can fill up your page at every junction here and put the direction of the slope at that point. Okay? That is basically what they mean by the direction field. Okay? And you've got your book, but you don't have yours with you today, right? Okay, you got it online. Okay, good. You see that figure there, and you see all those little arrows at every hatch mark that you can plug. Do I want to do that? Do I want to evaluate that big, hairy, messy function at every point on the coordinate grid? No, not particularly. But guess what? They have computer programs that will do that for you, so let them do it and put these in. Now, just looking at these, all they're showing is a direction without any indication of magnitude. Seems like to me they should give longer lines to the ones that have large numbers, slopes, and but they're just giving directions here, which tell you something. And there you see they just picked out one to start with, the blue one up at the top, and just sort of follow the arrows in general. You don't know if that's exactly, but it sure looks like it could be. Okay? Then the red one, start somewhere further down the page where the initial is not horizontal, but a little bit below horizontal, and then just follow some of the arrows there. Line up as many as you can. Yeah, that's looking a lot like the curves we saw in Chapter 1. And those that go starting out even a steeper negatives curve there, then, yeah, go down that, follow the arrows, and you have at least a general idea of what some of those curves are like. There's an infinite number of the curves. Even if you used every arrow on here, there's still curves in between those curves. So, but you get the general idea of where they're heading. Okay? So let's look at example 1, which is dealing with an executive direction field. Okay? Here is our differential equation. dy dx is equal to 0.2 xy. Have we seen that somewhere before? I think we used this about 2 or 3 times in the first chapter. Okay? So if it seems like it's a little familiar, it should be. Okay? So we got dy dx is equal to 0.2 xy. Okay. Now, do you want to pick out a few arrows that you can draw in easily? Second? 2, 3. You want that? That's your XY pair, okay? She chose 2, 3, okay? What would be the slope? Okay, I found the point 2, 3. 2, 3. There we are, right there. Okay, what's the slope at 2, 3? Oh boy, these calculators slow you down, don't they? $1.2, very good. And that's a little bit above slope of 1.2, something like that. Okay, I don't draw very well. You want to pick another? I can't hear. -1.2, okay. Okay, -1.2, that's right up here. What will be its slope? -0.4, okay, so that's going downhill a little less than half. Now, I want to, yeah, and remember, I should have these about the same lengths because all these are directions. They're not a magnitude, okay. Want to pick another? $6, is that what you said? Okay. All right. That'll be I'll find it. -4, 6. I think that's it right there. All right, negative, ooh, that's fairly steep negative, so somewhere about like that. I don't know if I'm right, but you know, just get a general idea. Okay, you like to work way harder than I do. I'm going to do a few of these. Everything on the x-axis, y is equal to 0. 0, 0, 0, 0. See, you work too hard. Okay, but you do need some of those. You really do. But every one of these is a 0 slope. So I can draw those in pretty quickly without the calculator even, okay? How about the y-axis? Second? Those are zeros also because your x is always 0 on the y-axis, so that product is going to be 0 there too. So here's a bunch more, Okay? Okay, I've done the easy ones now. Okay, the rest of them are like you were doing. You pick and choose and go with it. But every one of those is like that. Okay? Now, I don't know if these are at all connected, but it sure looks like, and we'd have to fill in a few more things, that you could have a curve that does something like this, because it has a horizontal slope there. It could have something like that. Okay? And if you look at what they did, sort of a computer generated, yeah, you see the points you chose, we got right. Okay? A slight negative slope here, more positive slope there, very negative slope there. And sure enough, look at this. Now, these didn't all have to be on the same curve, but the general pattern was that. And you look at the solution curves down there, and sure enough, that's what they look like. Okay? And what we did before, and if you remember, when we actually showed that this was a solution, this one does have a solution. We'll learn how to do that in this chapter. The solution was y is equal to c e to the 0.1 x squared. That was our solution curve, and that, these curves would be like that. You choose c equal to 0, and of course everything's 0. And that's it right there. Okay? You choose c equal to positive numbers, and I think you get the ones up there. Negative numbers, you get the one down here, because your y's are negative and c is negative. Okay? This is always positive, so all that depends on the sign of c. So you get the curves there. And sure enough, they're a family of curves. They look kind of like, but they're not quite hyperbole. Okay? They're exponential functions. Not inverse functions, but yeah, that's what the family of curves look like. Now, we could have gone through and done, I did the easy ones, you did a few of the harder ones, but they're none of them that hard, and got the curves, the directional arrows, and put them in, and then imagine the curves that might go through those arrows. And my first imagination was not far at all from what they showed here. Okay? Now, that was example 1. All right. I think we'll use the same slide here. And let's do example 2. Use a direction field to sketch an approximate solution. Approximate solution curve for the initial value problem, dy dx is equal to sine y. Okay? And with the initial condition that y of 0 is equal to negative 3/2. Okay. Now, tell me something you know from this. What does that information tell you? Blah, blah, blah. No, more than that. Okay. Especially the initial condition. What does it tell you? Say again? A little louder. I'm hard to hear. Huh? Did I write it wrong?
No.
Oh, okay. What did you say?
I was saying, are you supposed to
I think you're getting there. What this tells you is a point that's on the curve, doesn't it? There's the x, there's the y. There's a point. I can plot that point. So I can start my curve. I got a single point. And what is that? Zero on x, negative 1.5 on y, right? There's a point on that curve. Okay, 0, negative 3/2. You know it's there. We're not going to have a family of curves. We're going to have one curve, and that point's going to be on it. Okay? Now, let's take this information and plug it in up there. When at this point, what is the slope of the curve there? What is the sine of the y value? Negative 3/2. Now, how do you get that? Pull out your handy dandy calculator, okay? And what mode did you better be in? Radian mode, absolutely. No degrees are mentioned here anywhere, so you assume you're in radian mode. So do the sine of negative 3/2. In radians. What is that back? Second? Well, do it in your head. No, I'm just kidding. Okay. 0.909. Okay, that's awfully close to 1, isn't it? So at that point right there, the slope is very close to a +1. Okay? Now, following my silly lead, okay, let's pick some other y values. Like when y is 0, the slope is second. Yeah, the sine of 0 is. All right, multiple choice, huh? Okay. You gonna let me grade your papers that way? Okay, no, yeah, it's 0. Sine of 0 is 0. So everywhere where y is 0, which is the x-axis, now these all aren't going to be on there, but every one of these, the slope is 0. Okay? I don't really need those over there, but one of these over here is probably going to be useful, okay, because it's heading that way. So you got a 0 slope here, everywhere, okay? Now, for some other y's, okay, you can choose, say, some other values that you know automatically, like pi halves. What is pi halves approximately? Pi is just a little over 3, right? And 2 is 2, so it's something a little over 1.5. Okay? And at pi halves, we know the sine is say again? I can't hear. What is sine of pi halves? One. Okay. So when anytime the y is near 3/2, a little bit greater than 3/2, you got a slope of 1. So I don't know if it's going to make it up here, but if it did, you'd have a slope of 1 every one of these. Now remember, we're not going to use all these. We're only going to use 1, but if you were up here, you would have. Now, that's what makes me a little suspicious. Go back and do your evaluation of, did you put a negative 3/2 in there when you did it? Let's go back and do sine of negative 3/2. I think you gave me sine of 3/2. Sine of negative 3/2. Oh, good. I was going to think my math is not very good here. Oh my, no, if you got 0.909, you must have been in radians. I mean, that would be way too. Okay, so this is about -1. And guess what? All those are about -1 every time it's there. Now, these are not important. That's the one we're interested in. Okay? So this sort of opens up another deal. We don't need to do more here, but when I was doing the other, I said, that's got to be close to a -1, not a +1. So, okay. Well, let's see some others, like pi. That's about 3.1415, right? 9.1434, okay. Pi is just a little more than 3. So up here, what's the sign of pi? Zero, very good, okay. So that'll be 0 everywhere here. Okay. Everywhere that y is close. Why am I drawing them there? Goodness gracious, sorry. Y'all awake yet? Okay. It's supposed to be a little more than 3, not 2.5. I don't know where that was coming from. A little more than 3, you got zeros there. Okay? And again, these up here, I'm not even sure they're ever going to get there, but, there's 0 here. So you see, you can do a lot of these on fairly little information. And at negative pi, guess what your sign is? 0 again. So down here, just past -3, you're a slope of 0 again. Okay. I don't think we'll need these back here because that's the one we're interested in. Okay. And then we could do a few more, like at -5/2, you would be at +1. I mean pi thirds. 3/2 pi is what I was trying to say. 3/2 pi, you would be at +1. So that's a little more than 4.5. So you'd be at +1 here. Okay. Now, I can't quite make out where this is going. It seems unlikely it would go down here and then point back up. So I don't know. Let's see, do they show on here? Yep. This is what it's doing. It's coming down here and approaching this and coming from here like that. It almost sort of reeks of a little bit of a tangent looking type shape to it, but it can't really go past here. Doesn't look like it could easily, because if it did, it has to turn around and go positive. So it looks like it's near 0 here, near 1 there, and then goes back to being 0. That, I think, is the one and only one curve. Up here, you have a bunch of other curves that did like this, but this one would be that particular curve. Okay? So that initial value problem. I did all those others just to get an idea of what's going on, and then looking at it saying, I don't see any way, but what? You see, these are 0 here, going slightly negative, near -1, and then going back towards 0. But in negative sense. And if they were to penetrate here, then they suddenly have to go back up. That doesn't seem like it. So it looks like to me they're stuck in between these two horizontal things, and they're going downhill like that. And that appears to me to be the one and only one curve that meets that condition. Okay? And sure enough, that's what theirs kind of looks like too. Okay. Now, they have a little remark here. They do say something about increasing, decreasing, and that's one of the big things you get out of this is that the slope of that curve is going to indicate whether the increasing function or decreasing function or constant. Okay? So, and sometimes it's about all it can tell you, but it can tell you that. But when looking at the remarks here, sketching a direction field by hand is straightforward but time-consuming. You better believe it. Probably one of those tasks about which an argument can be made for doing it once or twice in a lifetime, but overall more efficiently done on computer software. So let the computer do the walking for you. Before calculators, PCs, and software, the method of isoclines was used to facilitate sketching of these. And basically what an isocline is iso means same, and cline means elevation, okay, kind of, or slope you could think of. So that's what you did. That's what we were doing, finding those curves that had the same pattern of slopes, okay? Have you ever seen a topographic map? Topographic maps have lines, if things are getting steeper, the lines are real close together, flat, they're far apart, and you can't tell just by looking at it whether that's a mountain or a valley, you just know, but if you get the general trend of things, yeah, and then if they put the numbers on, you know exactly what they are. If the numbers are going up, it's a peak, and if it's going down, it's a valley, okay? The numbers are going down, and that's basically what we're doing here. If you've ever seen on the weather station or your weather channel or your weather report on your TV, when they show those isobars, those are same barometric pressures. They do the same type thing, okay? They encircle high pressure areas or low pressure areas. You can't tell what they are until you look at the numbers to see if that's high or low, but it's the same type deal, okay? You can have isotherms, equal temperatures, you know, and you can follow the progression there. So basically that's what you're doing. You're following slopes, okay? Isoclines. All right, so that pretty much is 2.1.1. Let's move to 2.1.2, okay? Okay. We're going to start with something pretty close to what we had before, but a little bit different. The one difference we're going to do is this is going to be a function of y alone, not of x and y, okay? That was a lot like our last one, which was a sine y, only a function of y, okay? So section 1.1, way back in the first chapter, we divided the class of ordinary differential equations into two types, linear and nonlinear. You mentioned those earlier. I think that was the first classification you gave. We now consider briefly another classification of ordinary differential equations, a classification that is a particular importance on the qualitative investigation of differential equations. In ordinary differential equations in which the independent variable does not appear explicitly is said to be autonomous. Okay? I hope that's how they pronounce it here. Okay? So something like that, where the independent variable is not part of the function, only the dependent variable. Okay? If the symbol x denotes the independent variable, then the autonomous first-order differential equation can be written as, your final answer would be f of y and y prime, because it's first order, that's equal to 0. Okay? So in other words, there is no x dependence. Okay? Or I like probably that form a little bit better. Now, frankly, I'm a little bit bugged. I think they used to do one of those F's a little f and one the capital F. So I don't think they're being very consistent here. Okay, but we'll let them get by without it. I think this is the one they used to do a capital F, but don't sweat it. Okay. We'll assume throughout that the function f in this equation and its derivative, f prime, that both of those are continuous functions of y on some interval I that you're interested in. So here are a couple of first order equations. dy dx is equal to 1 plus y squared. Okay? First order, because your only derivative is first derivative. Only derivative is first derivative. Autonomous in that the function over there has no x dependence, only depending on the y. Is that a linear? No, the y is squared. If either the derivative of y or y itself is any power other than 1, nonlinear. If that had been a 0.2 as an exponent, nonlinear. 1.2, nonlinear. 0.999, nonlinear. You know, it has to be a 1 and 1 only. If that had been a 1 plus x squared, no sweat there. Doesn't matter what the independent variable is, that would have been linear. This one just happens to be nonlinear. Okay? They weren't asking that. I just thought I'd throw that out for no purpose whatsoever. Okay? But that is autonomous. Okay? How about this one? Have we seen this somewhere before? All over the place. Autonomous or not? Not autonomous, because it does depend on x. Linear or not? Okay. Yeah. Huh? No. The only problem with is that it does have a product of x and y, and I can't remember if that knocks it out of being linear. I think it might, but I shouldn't have even asked the question, because it's, yeah, you should all be like a lawyer. You never ask a question you don't know the answer to. You know? So I think that probably would knock it out from being linear. But it is first order, but non-autonomous. So what difference does this make? Many differential equations encountered in applications or equations that are models of physical laws that do not change over time are autonomous. Okay? Now notice there they said change over time. What that means is that probably your independent variable is no longer x, but t. So if you had something that had a t dependence in it, it would change over time. If it doesn't have the t dependence, then it would not. So you want those that are, if they don't change over time, they are autonomous. Okay. Okay. So let's do a few here. Here's and you know, it doesn't have to be x and y, as you'll see right off the top here. dA dt is equal to Ka. Now we saw some that were fairly similar to that when we did that long blah 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 section on applications. This would be the rate of change of your amount is proportional to how much you have. So that's it right there. Autonomous or not? Autonomous, because there's no t over there on the right hand side. You're right. And this would be linear and first order. Good. How about this one? dx dt is equal to kx times n minus 1, no, n plus 1 minus x. Okay? What you reckon? It is autonomous because x, don't think x is always your independent variable. In this case, no, it isn't. It's on top. So it's independent. T is your, x is dependent. T is your independent variable. Just while we're here, linear or nonlinear? If you were to multiply this through, that'd be a kxn, no sweat there, plus kx, no sweat there, minus kx squared. Remember, x is your dependent. That would be nonlinear. Okay. That's not what this is asking about, but it's there. Okay? How about this one? dt dt. That sounds weird, doesn't it? Think of that as 1, except those are different t's. Typically, what does the capital T stand for? Temperature, small lowercase t, time. So what is the temperature changing with respect to time? It's equal to k times t minus tm. Okay? What you think? Autonomous? And it's linear, exactly. This is a constant here. The subscript means that's basically your ambient temperature. What's your difference in your actual temperature or ambient, that determines on how rapidly that's changing depending on the constant of proportionality. Okay, good deal. How about this? Back to an A, dA, and we're still hanging with T's here. These are all rates of some nature, is equal to 6 minus 1 over 100th A. Okay? What you reckon? Autonomous, and this one happens also to be linear. Very good. Not that you need to know that. Okay. But typically K's, N's, anything with a subscript are counted to be constant. The variable are the one of those two things, dependent, independent, and if it doesn't have a subscript, it just shows up there, then it's that second variable. All right, good deal. Now, let's think back to Cal 1, probably a little bit of Cal 3, somewhere back there. Critical points. What were critical points? You remember? What made them special? If what? Okay. Now, back in Cal 1, it was basically where the derivatives were equal to 0. Those were your critical points. This is remembering it a little differently, saying where your zeros. And that's fine too, because guess what? You're dealing with the derivatives, okay? So, in a sense, it's the same type thing. But they're talking about where the point is a 0 of the function. They're calling this real number C to be a critical point of that. A critical point is also called an equilibrium point or a stationary point. Okay? Now observe that if we substitute the constant function y of x equals c into that first equation we had, that was dy dx is equal to f of y. And if that f of y, I'm sorry. Yuck. Okay. If that f of y was a constant, okay? So what does that tell you? The slope is a constant slope. Guess what? That's going to be a linear function. Only functions whose deal is there. So why are they saying that? No, I'm sorry. That's not what this is saying. It's not the f of y, sorry, because I was saying that doesn't seem very relevant here. Okay. It's saying the y itself is a constant. Okay. Sorry about that. That y of x is equal to a constant. Okay. Then what is dy dx? 0. Okay. So that means that your f of c, I probably should go back to this form, dy dx is equal to f of c. If that f of c is 0, that means c is a critical point, the derivative of the function there. So yeah, this is the same as what we were talking about before. Okay? So a critical point is also blah, blah, blah. Okay. If c is a critical point in this kind of form, actually I probably should, okay, I was doing two things at once there. There is that's an autonomous function. If the y is a constant there, then the dy dx would be 0, so that would then be a critical point at that value of y. Okay? If c is a critical point in this function here, that one right there, then y is equal to c is a constant solution of the autonomous differential equation. Okay, so what? A constant solution, y is x equals c, is called an equilibrium solution. Equilibria are only constant solutions of that original function. Okay, as I already mentioned, we can tell when a non-constant solution y is equal to y of x of 2 is increasing or decreasing by determining the algebraic sign of its derivative. In the case of this one, we do not need, we do this by identifying the intervals on the y-axis over which the function is positive or negative. So it's sort of a lot of blah, blah, blah there, okay? Let's look and see if we can figure out what it means. This is example 3. And you know, I think I'll go back to the previous, and let's see if we can do this here. Okay. Here's a differential equation. dp, pretty sure it's dt, is equal to p times a minus bp. All right. Sorry. What kind of equation is this? Differential equation? Second? It's an ordinary differential equation. No, it's not, because if you multiply through p, yeah, you're going to wind up with a p squared. So that won't be linear, but it's okay. We can deal with nonlinear. Okay? What's the new word we came across? Oh! Is it autonomous? Yes, it is. A and B are constants. They have nothing to do with the t. Okay? So only depends on the independent variable. I mean the dependent variable, not the independent variable. Okay. So there we have it. A and P. And they also tell us A and B are both positive constants. They didn't have to tell us that, but they did. Okay? Now, it is autonomous. They agree with us. Good. Okay. Now, what else do we know here? We know that when p is equal to 0, what's your slope of that function? By the way, when you do this, this is your p-axis, this is your t-axis. Remember, dependent vertical, independent horizontal. Okay? Okay. What is special about when p is equal to 0? Yeah, the slope is 0, right? Okay, absolutely. That means if the slope is 0, the function p has to be a constant. Well, if it's 0, it's a constant. So anytime p is a constant, the derivative of p is 0, but that means either p is equal to 0, and that would be, when p is equal to 0, that would be down here, and the slope is 0, okay? But that's not the only place where that's 0, because when a minus bp is equal to 0, your slope is also 0 there, meaning it's another critical point, okay? So, when is that true? If you write this as a is equal to bp and divide by b, then when p is equal to a over b, you also have a critical point. Okay? Well, they didn't tell us anything about a and b except they're both positive. So the ratio is positive, obviously, if both of them are positive. And they don't tell you whether a is greater than b or less than b or whatever. Let's just assume it's greater than b, somewhere right up maybe here. This is the value where p is equal to a over b. And we know the slope is 0 there too. Okay? Now, what we typically do here is pick some other values. Okay? All right. These critical points where the slope is 0, here's another assumption here, I think is something we've already covered. P has to be continuous. P has to be differentiable. And its derivative has to be continuous. Remember, we assumed all those things. So, that means that P can't change signs when can't change its slope. Okay? Down here, this dp dt is either going to be plus or minus. 0 there, it's plus or minus here, 0 there, and it's plus or minus there. Okay? Should be obvious, right? Well, if we knew something else about any point, think of it as a test point. Let's just pick this point down here. If we knew, now here the t is 0, but the p is negative, okay? And if p is negative, then they didn't tell us whether the relative size there, but if p were negative, of course that's negative. If p were negative here, you're multiplying a minus times that, so that's positive, and this would be positive, but then this would be a negative slope. So this must be going downhill here. Everywhere below there is there. How about if it's between those two? Okay? Well, p is positive, right? So this is positive. What about this one? Now remember, p is positive, and b is positive. But remember that a over b is where it's 0. So let's think about that a minute. So this is some positive value. That's a positive value. Who wins here? Is A bigger than BP or is BP bigger than A? I'm not sure that we have enough information to tell that. So let's move on up to here. something greater than A over B. No, wait, yeah. If P is between 0 and A over B, so this is, say, A over 2B would be right in here, wouldn't it? Wouldn't that be true? A over 2B would be right here, right? So let's pick that point. P equal A over 2B. So this is A over 2B, okay? The B's cancel out, you get A over 2, A minus A over 2 would be A over 2, but A is positive. So you're guaranteed this to be positive here. Negative here, positive here, let's move up here. Now we know that P is greater than A over B. So let's make it 2A over B. It's got to be greater, right? Okay, so 2A over B, the B's cancel out, and this would be A minus 2A would be negative A. A is positive, negative A is negative. P is positive, so this thing's negative. So it's negative here, positive here, negative there. So you know these are critical points. That's where your slope is 0. Negative below here, positive here, negative there. Okay? Because this is an autonomous function, there is no t-dependence here. You can just deal with the p-axis, and that's going to give you just about everything you need to know. Okay? So, on the interval, your independent variable is t. So now these are given in p's. Anytime p is negative infinity all the way up to 0, your sign of f of p is negative. We just determined that. That means it's a decreasing function below there, increasing function between 0 and a over b, and then greater than a over b, it's got to be negative again. Decreasing function there. So, in here, your function is always going downhill. Always. Everywhere here is negative. Here, everywhere here is positive. But it's 0 there, so basically these are families of curves that 0 here, 0 there, so they have to be positive in between. And up there, you got the negatives again. Going to 0 all along there. Okay? So you basically already need to know what your curve is looking like. So figure 2.1.5, can you see that in yours? Okay, yeah. That basically is what I've drawn here, and we did some test points here, here, and somewhere up here, okay? And those were our test points, and sure enough, we saw what we did. That is called a one-dimensional phase portrait, or simply a phase portrait of the differential equation dp dt is equal to that. The vertical line is called the phase line, okay? What vertical line are they talking about? Oh, I guess they mean the p-axis there, the phase line, okay? Now, your solution curves, this is a different problem now, okay? I was thinking the next figure, 2.1.6, had to do with the first one. I don't see how it could, because now there are y's and x's again. So this is now a new subject, solution curves. Without solving an autonomous differential equation, we can usually say a great deal about its solution curves. Like I just said here, all these solution curves down here are negative slopes near 0 here, and doing something down here, we don't know what. These are all positive slopes here, 0 here, 0 there, but increasing in between, but always positive. And above there, you got the negative slope again, approaching that 0 slope at A over B. Okay. They're kind of saying the same things we did before, just with if you locate, like we did, 2 or 3, 1, 17 critical points where the slope is 0, okay? If you locate those, okay, on your phase, what do they call it, phase line, okay, then anything in between, you can determine the slope of the function there. So everywhere in between, those have to be the same slopes, okay, because there's zeros at those critical points, and they are same signs in between and outside those. You just have to determine what sign that is. And just like we did here, when you have the critical points here, you divide the whole graph. Now, t's can be anything they want to. In ours, these were always increasing here, decreasing here, decreasing here. Whoa. Something like that. That was sort of, that may not be how the curves look, but they're going in those kind of directions. So you basically are splitting the domain, so it's actually the range of p's, into, if you had 2 critical points, 3 regions, okay? Below the lowest critical point, in between the 2, and above the highest. If you had 3 critical points, below the lowest, in between the next 2, in between the next 2, and above the last one. You just always dividing basically the range of P into those regions, okay? And we call those subregions, okay? And exactly, okay, I'm sorry. I didn't notice, I just did example 4, okay? In the region 1 down here, we saw it has to be 0 here, but negative below. So the curves are doing something like this. In between, 0 here, 0 there, but positive in between. So the curves are doing something like that. And then above the A over B, we tested, we saw they have to be negative there, approaching the 0 A over B. So there's something like that. And that's exactly what they showed in example 4. Sorry, I jumped ahead. Forgetting, I thought we were going to do a different problem, but they use the same one we just had. Okay. I hate to say this like this, but the last time I taught this course, I went through this stuff in gory detail, and after I finished, I thought, what was the point of that, okay, of dragging it out that far? So this time, I'm sort of skimming and hitting high points. I just don't see a whole lot of reason to drag out and go into every little feature here. But anyway, maybe I should. All right, let's look at example 5. New example, different from before, okay? Here's a differential equation, dy dx is equal to y minus 1 squared, okay? What would be a critical point for that? Oh, what kind of differential equation is that? Yeah, that's dy dx. You're making fun of my writing, I can tell. Okay, yeah, I got it. Yeah, I'm not that sensitive though. Okay, so you go ahead. Okay, you know.
I don't know.
It's autonomous differential equation. I was originally calling it autonomous too, and my student in my last term class said, "Isn't that pronounced autonomous?" I said, well, yeah, it can be. So I don't know how you pronounce it in differential equations. So since he said it was autonomous, I said, okay, I'll call it autonomous. Okay. It's like the autonomic nervous system, so I'll do it that way. Okay. So it is autonomous or autonomous or whatever you want to call it. Anything else? except if you expanded that, it would be y squared minus 2y plus 1.
How I was thinking about.
Yeah.
I thought it was 3.
Okay. So I that's still considered nonlinear, though we aren't even messing with that now. I just thought I'd throw it out there since you had mentioned it earlier. But anyway, it's okay. And what is the critical point here? Critical point is when your first derivative is equal to 0. What makes that first derivative equal 0? Y is equal to 1. And that's the only one. Even though it's a quadratic, it only has one critical point. It happens to be a repeated, but we're not going into that at all. So y is equal to 1. Now, what kind of scale do you want me to use? You want me to use 1 block as 1, or 2 blocks as 1, or 3 blocks as 1? Huh? Okay. I sort of favor 2 here. So let's do, this is our y is equal to 1. 1, 2, 3, okay, -1, -2, -3, and so on. And you can do the x the same way if you want to. I don't think it matters, because this is now x, this is y, because this is dy dx. So this would be a -1, -2, -3. Okay. Just so it's not so close to this thing. Okay. Now, we only have 2 regions. We know the function has a 0 slope here, at y is equal to 1. Okay? We don't know what it has anywhere else, or do we? Okay? How about when y is equal to 0? What would be your slope there? Positive or negative? Positive. So we know it has a positive slope when y is equal to 0. So this is plus down here. How about when y is greater than 1? Let's just choose 2. What's your slope there? Positive again. So you have a region here, but you have positives on both sides. Okay? Meaning the function is always increasing. Okay? But we have some sort of a deal here at y is equal to 1 where it has to be 0. Now, it has a single critical point, y is equal to 1, and from the phase portrait we conclude that y of x is an increasing function in the subregions less than 1 and greater than 1, okay? And this is for all x's, from minus infinity to positive infinity. For an initial condition, what they tell us here, why didn't they tell us at the beginning of the problem? I've been trying to find that. Y of 0 is equal to y naught, but this y naught is less than 1. Okay? Now we don't know if it's -17 or if it's 0.9. I mean, either of those would be less than 1. We don't know, we just know it's less than 1. Now, a solution, y of x, is increasing and bounded above 1. So y of x approaches 1 as x approaches positive infinity. Okay, what's it saying there? As x is approaching positive infinity, you have to be going toward this 1 because it's an increasing function. Okay? What that is telling you is that your function, and you don't know where it begins, so they're going to have to give you a little more information than this, but let's just say it's going to be doing like that. Okay? Now, I don't know where that begins. It's a whole family of curves. You have to have something else. But the y at 0 is some y sub 0, but that's less than 1. So you're somewhere down here. So wherever that is, it has to be approaching that. It has to have a positive slope here, and it has to be approaching that. So it could be a whole family of curves here that if this was, say, a -3, I used a -17 before, but then it would be something like this. If it was a 0.9, it's still like this, okay? So your function has to be approaching that horizontal asymptote because the slope there is always 0, okay? So it has to be approaching that. And they told us that y of 0 was some value y, but less than 1. So that means it's somewhere down here. So that y0 is somewhere on the y-axis here, and it's got to be a positive slope, so it's got to be approaching that as a horizontal asymptote. Okay. Well, if that's the case, then somewhere over here, remember it's still positive, it has to be going like this, okay? Now, can't have the same value here, so you see this one up here can never reach 0 because at x equals 0, this y is something less than 1. So you're somewhere down here, so it can't be up here. So this is going up like this somewhere because it's always a positive slope, but it can't reach that. Now, we don't know how close it can get to it, but it can't ever reach x equals 0. Because x equals 0, the y value is less than 1. So it's down somewhere down in the lower quadrant. Okay. Now, I don't know why they do this. It's not at all clear that talk about the same problem, except it's written here. But they just come up with this: y of x is equal to 1 minus 1 over x minus c. No, x plus c. Okay? That's a one-parameter family of solutions of this differential equation. Okay? They just pulled that out of the air somewhere. Okay? But they did give it to us. Okay? And they say see problem 4 in the exercise set 2.2. So it's yet another section away and a problem that I wouldn't normally assign because it's even. Okay? A given initial condition determines the value for C, and for initial condition, say y of 0 is equal to -1, which is going to be that one right there. Okay? Then we have a new problem here. Okay? If y of 0 was equal to 2, which is greater than 1, then we would be somewhere up there. Your whole problem shifts. Okay? So for the first case, where it's this one, it has to match here. Y of 0, they just told us was equal to -1, and that's equal to 1 minus 1 over C. And you know that's equal to 1. So, no, it's equal to -1. Y of 0 is -1. Okay? because when you put an x equals 0 in there, okay? So what do we have then? Let's solve for c. Let's add 1 to both sides and subtract and add 1 over c to both sides. Okay, so that gives us 2 is equal to 1 over c. So c is equal to 1 over 2. C is equal to 1/2. Okay, multiply both sides by c and divide by 2. C is equal to 1/2. So now I kind of hate. You would almost have to reinvent the wheel, but they let C represent those constants. But earlier they were calling them critical points, C. These are different C's, okay? The critical point here was 1, okay? That's that C. This C is the C that's your constant, integration constant. I'm sorry they use the same letter. I mean, it's not like we don't have 25 other letters they could have used. They just happen to use the same letter twice. Okay. So anyway, that says that the C equal 1/2. That means that your we haven't quite established what it means yet. But if it goes through here, then their implication here is this is a vertical asymptote. I usually do those in red. If that is the case, then this is what your thing looks like. Forget the others. They were all possibilities, but not anymore. Okay? We can even forget that. There it is. That would be your part of that curve. Okay? Now, since that's part of the curve, this is a vertical asymptote here, then this means, and here's why it's a vertical asymptote, because here's your solution. Obviously, x can't equal negative 1/2. If c is equal to 1/2, x can't be negative 1/2. That would make your denominator 0. So that's what makes it a vertical asymptote. Okay? So x can't be negative 1/2, so we have to do a vertical asymptote there. Well, from what you know about graphing rational expressions, this one would then have to be like this. So there is all your possibilities there. X can't equal negative 1/2 because your C was 1/2. And other than that, any xy there or xy there. Pick an x over here, you got to be up there. Pick an x over there, you got to be in that lower part because the slopes are always increasing. So it does tell you that. Now, what if you had chosen, what if you had been given an initial condition y of 0 is equal to 2? I'm going to do this in a different color. What color would you like? Blue, light, or darker? Light? Okay. We'll go with that blue. So this time we're going to have a different initial condition, and this would be y of 0, same everything else, is equal to 2, which, by the way, is greater than 1. So now we're up here, y of 0 is equal to 2. There we are. Okay? Not down here like we were last time, but up there at 2. Okay? Now, we're going to assume the same solution, that y of x is equal to 1 minus 1 over x plus c, where c is your constant, your integration constant. And we know now that that y of 0, that would be 1 minus 1 over c, is equal to 2, not the negative 1 we had before. So what we're going to do here, I think I'll add 1 over c to both sides. and subtract 2 from both sides, and that gives you, this is your equation here, this gives you negative 1 is equal to 1 over c, so c is equal to negative 1, right? So now your c is negative 1. If the c is negative 1, x cannot be positive 1. So now your vertical asymptote is over here. Okay? So again, your curve, this is going to be the blue curve, has to have the same constraints on it, but now it's going up like this, and this one on this end is going like that. So you just shift over to here by using a different different initial condition. That necessitates a change of c. The change of c moves your vertical asymptote, because you have one in this case, and then you have to match everything there. Again, it has to be positive here, so that means you had to have your vertical asymptote move somewhere here for that to be the case. And sure enough, that's where it lies. Okay? So use everything they give you, and it all depends on those c. That c throws out that infinite number of solutions that could have been anywhere in there and nails you in on one particular curve. It's two curves, but it's still one function, increasing function, as we saw. Okay. Now, interesting verbiage they use here: attractors and repellers. Okay. We got, well, I'll try to hang on 15 minutes. I really would love to take a bladder break, but I think I can make it. Do you need a break? You do. Let's pause just briefly. I know we don't. All right. So let's look at attractors and repellers. Okay. You know, I should have been doing the same thing they did. Like I say, my eyes have been sort of bugging this. I thought those were just dots there representing test points. They're not. They're arrows. Okay. Duh. Okay. In every case in this one, the arrow is up and up. Okay. That's what we determined by our slopes, meaning here the slope is 0, but they're up both above and below that. It just happened to be when I caught, I guess after drying or moistening my eyes when I was in the restroom, I see, those aren't just dots, those are arrows. Okay. So anyway. So I guess the little statement at the bottom of example 5 before you get to attractors and repellers says the solution curves are the portions of the graphs, and no, they're still talking about 2.8, 1.8. Never mind. The attractors and repellers, that's what those things are there. So let me clear this out. I don't think I'll need this at this point. Okay. So suppose that y of x is a non-constant solution for the autonomous differential equation given in equation 1. Equation 1, you have to turn back a couple of pages, and that's equation 2. Goodness, I think they mean 2. Because it's not, 1 is not autonomous, I don't think. Turn all the way back to 1, that's the f of xy. I think they mean 2 there, okay? and that C is a critical point of that differential equation. There are basically three types of behavior that Y can exhibit near C. Okay? So, let's just pick a C. Okay? How about right here? I'm going to stay with your blue. Is that all right? Because I use blue in the book. So there's your C. Okay? Now, and you only have the one C. Okay? So there's it says three types of behavior, but they have 4 lines here. So let's go with it. Okay. The first one that they show is up here is going towards C, down here is going towards C. Okay? Okay. If that's the case, then everything above C is decreasing, everything below C is increasing, so both things are going to C. Now C, remember, if that's constant, if that's a critical point there, that means you have a 0 slope there, okay? That's the whole definition of the critical point, a 0 slope. So that means things coming down here must be approaching that. Why that didn't draw, I don't know. And things from here must be approaching that. Now, they don't have to be so symmetric like that, but they're approaching there. Now, I'm assuming that's what they're going to call an attractor, okay? Now, another possibility, let's go with a different color. You pick me a color. Say again. Pink. Say again. Purple. Okay, that one right there. Okay, we'll go with purple. Let's say in the purple case, they're going away from C. Everything above C is an increasing function. Everything below C is a decreasing function. But at C, you have a 0. So that means your function is doing something like this in both directions. And I purposely didn't make those so symmetric anymore. So they are repelling from C, I guess. Okay, that's what I would call it anyway. Repeller in B, that's what they called it. Now, there's 2 other possibilities. The one we just showed, and I've already used blue, so give me a different one. Green, light or dark? Light, okay? Light green, okay? This one where they're both increasing here and increasing there. Well, we saw what that looked like. There must be some point here that, depending on what your initial condition is, that will determine if you have a vertical asymptote, but you must. This will either be like this and like this, something like that. You can't have, and I should have picked up on this a little earlier too. Really lousy examples because this is showing, yeah, the curve's going to be right here. But in this case, since they're both increasing, because any one function can't have 2 values, so it almost implies there's got to be a vertical asymptote there. Okay? And the last, give me one more color. Blue? Oh, red. Sort of the dark red or the red? Just the regular red, okay? On this one, now we've got the light blue was attracting, purple was repelling, green was up, so this one must be down. Okay, so the red is down above and down below. Okay, so what must that be doing? That must be coming in like this, and also I've drawn these backwards. Let me reverse that. Okay, If this is decreasing, then it would be coming down like this, but down like that. Okay? Now, those two conditions, for some reason they call them semi-stable. Okay? So that's why they said 3 types of behavior, but then they drew 4 curves. One is attractive, one is repeller, and so those are 2 types. The semi-stable would be on the up and up or on the down and down. Okay, so that would be, and they call that semi-stable. Okay. Now, now, what they never said, they gave this when you had the 1C, okay? They didn't talk in these same terms with other, if you had 2, 3, or 7 Cs, you know. I guess you referred to each C about what its activity is. A critical point C is said to be asymptotically stable. And using a physical analogy, the solution that starts near C is like a charged particle over time is drawn to a particle of the opposite charge. So C is also referred to as an attractor, and then that's asymptotically stable. When it's repelling, that would be your unstable. Okay? And then the other is called semi-stable because it's attracting one side but repelling the other. Okay. Now, anything coming in like this, whether it's the blue or the red or the blue or the green here, those are stable. They're asymptotically stable. Okay? These going toward some vertical asymptote are unstable. They aren't going to, they're moving without bounding. Okay? This would be, that would be, and these 2 would be. Okay? But if you have one that's going stable and one not, that's semi-stable. Okay? I've been trying to think through and see if this relates to stability you talk about in physics or quantum mechanics or just about any of those areas. And it may have some pertinence to it, but I don't think it's direct. Okay? I don't know if you're familiar with, whoa, we're out of time, with those forms of stability, but I've often seen this won't be good, but this would be a stable state. You perturb it a little bit, it tends to go back to the state. Okay? Now this won't be a great example, but this would be quasi-stable. It somewhat is, but if you give it a little more, it does more because of this is fluid. This would be unstable. It's never going to. So I don't know if these stabilities refer to the same thing. This is a physics you call stable, unstable, and this would be quasi-stable. Okay. Not the greatest example, but that's. And again, I've been trying to think through and see if these stabilities refer to that, and they may, but I can't see a direct link, so I probably shouldn't have even mentioned it. Anyway, we'll start next time on page 43, autonomous differential equations and direction fields. Seems like we've been there, done that, but they're doing them again. So there'll be a little bit more we can glean from that. what you can do is homework exercises here. Oh, we almost finished 2.1. Look how close we got. You can do either 1 or 3 or both. Any of the odds 5 through 11. I would do 13. 15. Whoa. Basically, oh, that's 2.1.1. Yeah, we did all those. Then there's some discussion problems. You can think through those or whatever. They mention a null climb there. If you're interested in going there, go for it. Okay. 2.1.2. Trying to remember which one we are. Yeah, that's where we are now. Okay. You can do 19 and any of the odds 21 to 27. And I'd say stop there. I'll add 29 later. Okay. All right, good deal. Guess what? I hope for the rest of the term we will meet twice a week every week. So far this term we've had 4 weeks. First week we started on a Wednesday, so we didn't meet but one day. Second this class met Tuesday. We met twice 2 weeks, yeah. My Monday, Wednesday class has only met twice a week, one time. 1 week out of 4. This one has met 2 out of 4. Okay.
I was going to let you know that I won't be here Tuesday.
When?
Tuesday.
Tuesday. Okay. All right. Well, I hope to be recording like always. So.
Yeah, I guess.
Okay. Good deal. And I thought we made decent progress.